Welcome to this explainer. Have you ever actually stopped to think about how we've engineered these brilliant solutions to move massive, truly massive amounts of data across physical networks without the whole system just crashing down? Well, if you've ever plugged in a network cable or wondered how your office network handles so much traffic so flawlessly, you are in the exact right place. Today, we're unpacking the magic behind Ethernet, local area networks, or LANs. We're going to break down the physical layers and those underlying standards that make modern digital communication possible. Here is our roadmap for today. 1. The birth of Ethernet. 2. Decoding the 802 standards. 3. UTP and fiber optics. 4. Baseband versus broadband. And 5. Boosting speed and distance. Let's get right into it. Section 1. The birth of Ethernet. To really understand how our modern local area networks operate today, we've got to rewind a bit. Ethernet didn't just magically appear out of nowhere in the early 1980s. It was actually developed at the legendary Xerox Palo Alto Research Center, you probably know it as PARC, by brilliant minds like Robert Metcalfe and David Boggs. But, an invention sitting in a research lab isn't exactly a global standard yet. So Xerox teamed up with Intel and Digital Equipment Corporation. They called themselves the DICS Consortium to create the Ethernet I and Ethernet 2 standards. But the true stroke of genius, the thing that made Ethernet's global adoption possible, instead of keeping it proprietary, they handed the development over to the IEEE to make it a universal standard. Section 2. Decoding the 802 standards. So, when the IEEE took the reins, they had a massive headache on their hands. How do you make absolutely sure that a device built by Company A can actually talk to a device built by Company B? To solve this, they set up the 802 LAN/MAN Standards Committee, which then spun up specific working groups. Now, engineers aren't exactly known for their poetic naming conventions, right? So we end up with these very literal, kind of bureaucratic numbers. We've got 802.1 for general standards and security. We have 802.11, which you probably just call Wi-Fi, and 802.16 for WiMAX. But the one we really care about today is 802.3. The 802.3 working group is entirely in charge of creating Ethernet standards. In fact, today, if you say 802.3 or Ethernet, you're basically saying the exact same thing. Now, these Ethernet standards govern OSI Layer 1 and Layer 2 processes, which really just means the actual physical wires and the basic data framing. But they aren't just abstract ideas floating in the cloud. They are implemented right on physical hardware, like a network interface card, or NIC. When the 802.3 working group finishes up a new standard, vendors immediately rush to build compliant products like this card, which is what allows your computer to actually plug into the network and start talking. Section 3. UTP and fiber optics. All right, so the NIC fires the data out, but what exactly is it traveling through? We've basically got two main highways here. On one side, we have unshielded twisted pair, or UTP copper wire. You'll see this in standards like 100 base TX and 1000 base T. These are super inexpensive, and they totally dominate those shorter access links that connect your computer to the wall. But there's a catch. They max out at exactly 100 meters. When you need to go further, say connecting two server rooms or bridging entire floors, you need trunk links. That's where 1000 base SX steps up. The S actually stands for short wavelength light, specifically 850 nanometers. This multi-mode fiber standard pushes 1 gigabit per second speeds over much longer distances, anywhere from 220 to 550 meters, depending on the fiber's core diameter. So the takeaway here, engineers are always doing this strict balancing act between cost, speed, and distance when choosing a medium. Section 4. Baseband versus broadband. Now, you might have noticed that all those standards share one specific word, base. Think 100 base TX or 1000 base T. That base stands for baseband transmission. In baseband transmission, the signal is literally just injected directly into the wire or the fiber cord, and then it simply propagates down the medium. There's this beautiful, clever simplicity to it. It doesn't require translating the data into some complex array of radio waves. It's just pushing raw electrical pulses or light flashes straight down the line. So why did baseband totally take over Ethernet? Well, it all comes down to cold, hard economics. Because the signal is simply injected into the wire without any complex alteration, the equipment is incredibly cheap to make. Contrast that with broadband transmission. In broadband, the signal has to be specifically modulated to propagate in different radio channels. That requires way more complex and, frankly, much more expensive hardware. Because of that, broadband is super rare in standard Ethernet LANs, although you definitely see it in outside services like your home cable modem. Ultimately, baseband became the undisputed champion of the local network simply because it was cost-effective and it just worked. Section 5. Boosting speed and distance. But hey, what happens when what works just isn't cutting it anymore? Networks hit physical limits, right? Cost constraints, speed caps, signal degradation over long distances. Just imagine this scenario for a second. Your network demands are absolutely exploding, and suddenly you need 1.7 gigabits per second of bandwidth between two switches, but you only have a 1 gigabit connection using a 1000 base SX fiber link. The obvious answer is just upgrade to a 10 gigabit port, right? Sure, but that is terribly expensive. Instead, engineers use a trick called link aggregation or bonding. Think of it like a highway. If traffic is backing up, you don't necessarily need to build a brand new, wildly expensive superhighway. Instead, if your switch supports it, you just pave one more standard lane right next to the current one. By bonding two 1 gigabit ports together, you instantly get 2 gigabits per second of capacity. It is a brilliant, highly cost-effective workaround to bypass speed caps without entirely wrecking the IT budget. Okay, but what about distance? As a signal travels down a UTP copper wire or a fiber optic cable, it gets tired. It suffers from propagation effects, meaning it weakens and gets distorted. If you just send it through a simple connector onto another wire, that distortion continues until the data is completely unreadable. But Ethernet switches are smart. They don't just pass the signal along, they regenerate it. Think of it like a relay race. The original signal sprints down the first link. By the time it reaches the switch, that received signal is exhausted and degraded. But the switch reads the ones and zeros, and instead of just handing off a tired signal, it creates a brand new, perfectly polished signal and sprints that down the next leg of the race. And this right here leads us to a seriously wild reality of network architecture. Because every single switch along the path receives the degraded signal, cleans it up, and regenerates it flawlessly, those propagation effects are completely zeroed out at every stop. So while an individual physical cable might have a strict limit, like that 100 meters for UTP we talked about, the overall station-to-station data link between computers theoretically has no maximum distance at all. Data can bounce across a series of switches endlessly. It can effectively travel infinitely across a network. Which brings us to what's next, the future. The IEEE, they're absolutely not slowing down. We're already seeing standards like 802.3bm defining staggering speeds. We're talking 40 gigabit and even 100 gigabit Ethernet running over fiber optic cables. As our hunger for data just keeps growing exponentially, and fiber technologies become cheaper and more accessible, we really have to ask ourselves, will those traditional unshielded twisted pair copper wires that dominate our access links today soon become actual relics of the past? It's a provocative question for sure, and one that just highlights how dynamic and ever-changing the world of network engineering truly is. Thank you so much for joining this explainer. I really hope this helps you look at that network cable plugged into your wall with a whole new level of appreciation.